Uh, Hello everyone, welcome to all of you in my lecture today. So here in this lecture, I'm going to discuss about some important topic of mass transfer, which is very important for GATE examination. So the topic is subcooled reflux and open stream or direct stream in a distillation column. So, my dear friends, here, in general, the reflux which is going to enter into the distillation column that should be at its saturation point. Okay, right? That liquid should be at its saturation point. But sometimes what happens, it doesn't used to be on the saturation point. So there may be some deviations or some circumstances that arises that reflux may be subcooled. So the reason behind that subcooled reflux is vary from different condition. But here I have categorized three main reason for the subcooled reflux condition. That is, if the bubble point of vapor is significantly greater than the subcooled liquid temperature, then the reflux will be a subcooled reflux condition. Next is if the condensate exit pressure is lower than the pressure at the top of the tray. So here you can see how this happens. So here if you talk about here if it is our condenser, right, and here if it is our distillation column, so it is coming to the condenser, and here it will be coming and going to back. So here this will be L naught and here it will be. So if condenser exit pressure is lower than the pressure at the top of the tray, at the top of tray here, so then in that condition the reflux will be subcooled reflux. And third important is, if by any means if there is a heat loss in this particular line, if there is any heat loss in this particular line, so that may causes the sensible heat transfer to the environment from this particular reflux, and it will get subcooled. So I have discussed about the theoretical concept of the subcooled reflux. Now I'm going to derive the mathematical relations for the subcooled reflux, right? So try to understand here. If we draw the distillation column here, this is a distillation column. So here feed will be entering to the distillation column, and here there will be a tray for the distillation column, and so from the top it will be coming to the condenser here, and a part of this condenser will be going for the distillate, and a part will get returned back to the top of the distillation column, right? And this is a reboiler, so here it will be W, and here a part will get returned back to the V bar and here L bar. So this schematics you all knows. I'm not going to discuss all these part. So here it will be V, here it will be L. So if temperature of this reflux is assuming I am is assuming T, and if temperature inside the distillation column at its bubble point, if liquid is at its bubble point, so if this is coming into the distillation column, if it is subcooled, then what will happen? A part of this vapor will get condensed on the top of the distillation column, and it will be coming to the this particular plate. So my dear student, what will happen? A part of this vapor was leaving to the plate, so a part of this vapor will get condensed as a form of delta L. So I'm assuming delta L amount of this vapor is getting condensed. So here what will happen? L is equals to L naught plus delta L. L is equals to L naught plus delta L. So here this is L naught. So this L naught will be coming to the distillation column, and again this vapor is also getting condensed. So this total L in the this L will be at this particular plate. Any nth plate, I am assuming this is nth plate. So L is equals to L naught plus delta L, right? So I am assuming this is equation first. So this is material balance. Now if we try to do the energy balance here. So what we can do, see. So here this delta L naught is getting condensed into vapor to liquid. So what will happen? So the amount of heat delta L multiplied with lambda of B, that is equals to what? L naught Cp of L, and what will happen? Tb minus T naught, where I can write Tb is bubble point and T naught is reflux temperature that will be given in the problem. So from here, can I calculate that is delta L, that will be equals to L naught Cp of L, and that is Tb minus T naught, and divided by lambda V, that is latent to vaporize. So we have calculated the value of delta L. So from here now, can I calculate that is L, that is equals to delta L plus L naught. So we can write delta L, L is equals to that is L naught Cp of L, and here it will be Tb minus T naught and divided by latent heat of vaporization plus L naught. So if I take common, that is L naught, so we can write it here L plus Cp of L Tb minus T naught and divided by lambda V. So if I am assuming this is equation first, uh, equation second divided by D. So what will happen here? So L upon D, that is equals to L naught upon D, and that will be equals to 1 plus Cp of L Tb minus T naught and divided by lambda V. So here we can see that L by D, that will be called as R dash, that is equals to R into 1 plus Cp of L Tb minus T naught and divided by lambda V. So that this is very important relation. This is very important relation that I mean you need to understand. So basically, I will always suggest you to I mean understand the parts of derivation of this particular problem, because sometimes you forget this formula. So better to do the derivation. Try to understand the derivation. So here I have derived that R, that is R dash, that is equals to R into 1 plus Cp of L and Tb minus T naught upon lambda V. Now understand this is R dash, that is called as the internal reflux ratio. So in the problem, it will be called as calculate internal reflux ratio. Then you will have to calculate R dash, and R, this is called external external reflux ratio, right? So these two things was very important, and Cp is the latent heat of vaporization of that column liquid, right? Tb is the bubble point, T naught is the. So I am assuming case first. If Tb is greater than T naught, so R dash is greater than R, right? R dash will be greater than R if Tb is greater than T naught, because Cpl by lambda V is positive, so 1 plus something, right? And if I am assuming case 2, if Tb is equals to T naught, if feed is hinting at its bubble point, it's very important, that used to happen in most of the time in the distillation column. So what will happen? That is R dash is equals to R dash is equals to R. And next, third important point is if Tb is less than T naught. So if Tb is less than T naught, I mean, what will happen here? Already reflux is below its bubble point. Then it will be like whenever, just like what happened. So you can write R dash is equals to R into 1 plus Tb minus T naught Cp of L upon lambda V. So all both whole term will becomes negative, right? So this whole term becomes negative because TB is less than TL. So R dash, right? So R dash will be less than R. R dash will be less than R. Why? Because this will be a negative. So can I write R dash is equals to R into 1 minus something of A, if I am assuming this is A. So that is equals to R dash is equals to R minus AR. So if we are subtracting something from R, that's why R dash will be less than R, right? So this is the three important points that that you may get the problem from this particular point. So I'll suggest you to keep all these things in mind whenever you are trying to understand the subcooled reflux. Now Next topic of discussion of this video lecture is use of open esteem. So one more important thing that I would like to say you here. So whenever we are trying to calculate the composition in the stripping enriching section of the distillation column, that used to equal the equation of operating line of the enriching section is equals to n plus 1 is equals to r upon r plus 1 xn plus xd upon r plus 1, right? So I am assuming this is equation 4. So if, I mean, whenever the reflux is entering at its subcool condition, so you replace r with respect to r dash. So you here you can write that is yn plus 1 is equals to r dash upon r dash plus 1, and the equation will be as it is. You don't need to change anything. But here, due to subcool reflux condition, your reflux ratio will get changed, and due to this particular reason, so this will be your conditions of a reflex condition. So one more important thing is that, so if your distillation columns operating line equation is like that, right? uh, so if r dash is greater than r at subcooled reflex condition, at subcooled reflux condition, so in that condition what will happen, try to understand one thing. So if this is the equation of your at operate r, now since r dash is greater than r, so slope is what r dash, here it is slope that is equals to r dash upon 1 plus r dash, right? So in that condition what will happen, the operating line will be like that. So here it is r, here it will be r dash, right? Slope here, slope that is equals to r dash upon 1 plus r dash, right? And here slope will be r upon 1 plus r. So slope will be more for subcooled reflex condition as compared to the normal reflex condition, as when the reflex is entering at its bowl point, right? So I hope this topic is clear to all of you now. So I am moving towards the next topic of this discussion of the lecture, that is use of pen steam. So it's a very small topic, but sometimes you may get question for 1 marks in the gate. So I am just discussing use of uh, use of open steam in the distillation column. So basically, sometimes it is called as open steam, or sometimes it is called as uh, direct steam condition, right? So basically, what happens in the distillation column, whenever we want to distillate any product from the distillation column, continuous distillation column, in that column, feed will be entering, and the heating medium used to be heater, right? But here we are not using heater in the open steam distillation column. Irrespective of heater, uh, the use of direct steam is recommended here. So I am assuming this V bar is the molar flow rate or mass flow rate, you can call it, with respect to your units in the problem. That B bar is equals to the steam flow rate, right? I am writing here it is steam flow rate, and you check the unit in the problem, which problem types of unit is given, either mass flow rate. So unit will be in kilomole per hour or kg per hour. That depends upon the unit of feed, right? So try to make the unit same for everything. And here I am assuming it is W, uh, that is bottom product, and sometimes it is called as the residue in technical term, that is in the industry, right? So residue. So here it will be a condenser where the top product of the distillation column will get condensed, and part of this liquid, part of this condensate will get returned back to the distillation column, that is called as L. This is called as the L, and here it will be called as the D. And the composition is here is XD. Here composition I am assuming is ZF, and here composition is XW, right? That is composition of more volatile component, that is ZF, XD, and XW. So if we apply the material balance, overall material balance, so can I write F is equals to D plus W, that is equation second. So you all know the material balance of the distillation column. Why I am assuming this material balance? So this will be total material balance, like that. of this envelope. So here that will be open stream is also going through this. So here it will be V bar plus F is equals to D plus W. Now you can write that is component balance. Component balance. So I am assuming the component balance of the more volatile component. So can I write here that is F into ZF plus V bar into 0, because this is only a pure open stream. There is no any uh, quick component present in it. That's why V bar into 0, that is equal to D into XD plus W into XW, right? So here it will be equals to 0. So can I write, if I want to calculate the composition of the residue, so you can write XW, that is equals to F into ZF minus D into XD upon W, right? So now here you can also substitute W is equals to V bar plus F minus W. So these two equation you can couple, and after depends upon the requirement of the calculation of the parameters in the problem, you can calculate anything. Okay, so this was the very small topic of open distillation. So with that, I'd like to end the meeting today. So all the best.